See if anyone's coming in. Okay. All right. Welcome back to S.T.E.M Online Academy. For those of you who don't know, my name is Jason Mastorakos, and I am an author of the book Advanced Integration Techniques, and also a tutor in advanced mathematics and physics. Our channel, my channel specifically, is mainly about cultivating your mathematical intuition and rigor. And I do that using a very special procedure and technique that helps everyone learn advanced, well, not everybody, but most people learn advanced mathematics using a schematic. One is using, making sure that you have a strong foundation in the subject material, okay, whatever it is. That's obvious. You need to have a strong foundation in whatever you're doing in order to understand it. Number two is to translate whatever problem you're doing into some sort of graphical model or a geometric model of some sort, so you can see what is happening, okay? And not just that, you can make the math come alive, right? So by using models, by using graphs, you can see the math come alive. And it's also a good comparison for step 3 when you try to solve a problem, which is using some sort of mathematical method, okay? That's where the algebra comes in. The point being why I use this 3-tier method to solve problems is because number 2, step 2, is good because it gives you a comparison, okay? Something to compare your results to see if you're on the right track, because quite often people don't know if they're on the right track for solving the math problem. So if the graphical approach and the algebraic approach match, then more likely you have the right answer. So there's consistency there, okay? All right, so as I mentioned, welcome back. I wasn't available Sunday. For those of you know, usually I do Sundays, Wednesdays, and Fridays. I was busy last Sunday, so now I'm back into the swing of things. Okay. Now today, what we're going to do is we're going to continue from the book, my book, Advanced Integration Techniques, where we're going to be looking at once again the gamma function. Okay. So I'm sure the people who've seen my videos already have seen what I'm doing, mainly going through the book lately. Before that, I was doing other, just like math and physics in general for students. By the way, this is for undergraduates, right? So it helps if you have a strong foundation in integral calculus and linear algebra, please, in order to understand the videos. Okay, so that's what we're going to be focused on. Okay, is another another section of the book, okay? And it's going to be the gamma function. Now, as I mentioned, I did talk about the gamma function before, okay? But this is going to be a more in-depth and rigorous deep dive into the gamma function, okay? So this is going to be the most, the clearest, most rigorous, and most intuitive lectures so far that I've made, okay? So for those of you who, as I said, are interested in this stuff, you will enjoy it a lot, okay? So let's get into the gamma function. Okay, so let me go to the share screen. Okay, so let's go to share screen here. Okay, so let's jump right into it. Okay, we're gonna go to the whiteboard. All right, so this is the gamma function, and I like to call this the title, the deep dive into the gamma function, okay? So as I said, part of today's menu, right? I overviewed, welcomed myself, right? We're going to talk about what is the gamma function, like what it really is, okay? Why gamma of n is equal to n minus 1 factorial, okay? So how the gamma function relates to factorials. Graphing the integrand, right? I mean that product of the integral, okay? The integrand is the function inside of the gamma function. X to the z minus 1, e to the negative x. Number 5, the half integer miracle, I like to call it. So gamma of 1/2 is equal to root pi. Why that's the case, okay? Number 6, the Gaussian integral plus pi connection. Number 7, we haven't delved into this before when I talked about the gamma function is going to be the reflection formula. Okay. We're going to go deep into that. Okay. Actually, we'll even discuss a proof that I want you guys to try. Okay. I'll discuss it maybe for homework as well. Let me see if anyone's coming in. Okay. All right. And then number 8, differentiation under the integral sign. Okay. We're going to discuss what I mean by that. I also did a video about Feynman trick, okay, the differentiation of an integral sign. But here it's going to be more about applying it to the section of the book that we're doing, the gamma function. Okay. Number 9, asymptotics and Stirling's formula. Number 10, physics applications to PDEs, quantum physics and probability. And number 11 will be take-home problems, viewer research problems for you guys to do, for anyone who wants to come in and want to do the challenge problems. Okay. As I mentioned, all this stuff is in my book, minus the maybe at least 3 of the viewer research problems. They're highly related to the problems in the book, but they're not the exact problems. Okay. All right. So that's what we're going to be talking about. Let's get right into it. Okay. So does anyone know what is the gamma function? Okay. Anyone in the chat know what the gamma function is? I'm going to take a guess. For those of you who already know, go ahead if you want to or not. But for those of you who don't know, just pay attention, right? Okay, so the gamma function. All right, so what is the gamma function? Guess. Anybody? Okay. Oh, and by the way, some of you might be asking for who've seen my videos before, why am I going back to the gamma function if I've already done quite a few videos? It's to reiterate some things in more of a rigorous detail and to combine different ideas from not just the book, but mathematical theory in general. Okay, so you're going to see how the gamma function mixes with Fourier transforms, and then Fourier transforms with the Gaussian integral and all of this, and maybe even some complex analysis, right? So for those of you who have seen my other videos, it will help for this one, preferably. Or if you're a person who's already mathematically strong anyways, and you're fine with almost anything, as long as you have a foundation in integral calculus, you'll be fine, okay? So as I said, we're going to talk about what is a gamma function, okay? So what is the gamma function? What is it? What is the gamma function? Anyone take any guesses? Gamma function. What is the gamma function? Okay, I'll spell it out. The gamma function, right, is denoted as this capital Greek letter, right, gamma of z that I've highlighted. Okay, so gamma of z is the gamma function. And it is a mathematical function, okay, which pretty much permeates between the concepts of the factorial, of a factorial, at least you know what a factorial is, and factorial, okay? Quite often it's used in statistics and probability. So with factorial, you should know factorials. If you don't know factorials or understand them, you may have a problem with this lecture, okay? So what a factorial is, right? N factorial, n by n minus 1, dot, 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 multiple products of n minus r plus 1, where r is some other term in the mix, right, of n minus r plus 1, okay, to the complex and real numbers, right? So that's what a gamma function is, right? Very clearly, it is a mathematical function which permeates or extends the concept of a factorial, both into the complex and real domains, okay, or complex and real numbers, as I've written it. Any questions on that? If anyone has questions. Okay. All right. All right. So that's definition 1. Okay. It's a very simple definition. I don't even need to say definition. Well, it is a definition. It's not exactly, I wouldn't say a definition for theoretical terms, but yeah, it's a definition. Okay. So that should be clear, right? A mathematical function that extends the concept of a factorial to complex numbers and real numbers. So what I mean is, in terms of factorials, right? It's related to that. We'll talk about that for those of you who don't know. Definition 2, right, is the primary definition of the gamma function, okay? So the primary definition of the gamma function for complex numbers z, okay? Anyone understand what I mean by a complex number? Okay, so complex numbers, right? Z equals A plus IB. A is a real part, B is an imaginary. If that's making sense for anyone who's coming in. Okay, any questions? All right, so for any complex number z, right? So as I mentioned, primary definition of the gamma function for complex numbers z, right, has a real positive part. What I mean by the real part is that the real part is just, as I said, z equals A plus IB. Okay, A is real, B is the imaginary part of a complex number, right? Okay, right, so z equals A plus IB, put it on the side here, where I'm highlighting A being real, right? Right, A is real, B is the imaginary, so M of z, real of z and M of z, if that makes sense, if there's any questions on that. Okay, is there any questions? Also going to be, I don't want to get too fast, I want to make sure that other people come in and hopefully chime in at what I have to say. Another thing too I want to mention is that this is a live show, right? So it doesn't make that much sense for me to keep jabbering, right? I want your input, right? So if you guys can give me your input, that will be very handy, okay? Because it's supposed to be a back and forth type of dialogue, right? To the best of our abilities to understand and communicate with each other. But that's how the learning builds, right? And so I want you guys to give me input, okay? On anything. You have any questions, anything that you want to figure out from the definitions, please let me know. Okay. So as I mentioned, right? Definition 2, okay? Primary definition of the gamma function for a complex number z. Right? So those of you who maybe had a brain fart and don't remember what a complex number is, it's always in the form of z equals A plus IB. Real part is A, B is the imaginary part on the imaginary and real axis. Okay. You should also know that a complex number is a vector, right? A complex number is a vector, right? Because it's at a specific coordinate vectors of A comma B. Okay. So again, with a real and positive part z has to be greater than 0. Okay. So in order for a gamma function to exist, right, for complex numbers, right, the real part has to be greater than 0. Of course, that makes sense, because if you don't have a real part for your complex number, you won't be able to get an integral, right? Okay, and it's an Euler type integral of the second kind. Okay, so as I mentioned, right, so it's an Euler type of integral of the second kind. So anyone have any questions just going into this? Okay, just want to see if you guys are understanding, right? So it's an Euler type of integral. By the way, yes, we're going to continue. Yeah, we're on the right track. So this is the order I want to go in, okay? So the primary definition of the gamma function, complex number z with a real positive part, where real of z has to be greater than 0. Now, the Euler integral, right, of the second kind, right, is gamma as a function of z is an improper integral of x to the z minus 1 power. By the way, z is a complex number again, okay? X to the z minus 1 times e to the negative x dx. Okay. I want to make sure you guys are understanding this conceptually deep, if you know what I mean. Right? What I'm trying to say is, I have talked about the gamma function before, right? And I've mentioned if some of you compared the past video on the gamma, like my past live or my past regular videos on YouTube on the gamma function, I would have said, you could also say gamma of n, where n is just some number, integer, does that be integer, real, rational, doesn't matter. Gamma as a function of n is the improper integral x to the n minus 1 e to the negative x dx, where n, okay, as I mentioned, it was a function of n. Here, it's a function of z, okay? So if any of you had any questions from before, new people, because you've probably also seen it written as gamma of n, and n is not a complex number. Z is, though. So you might be asking, how come you can have a gamma function for both n or z? Guess what? You can. It works for, as I said, real complex numbers or, rational numbers. All of these types of numbers, the gamma function is allowed to be used. You can take the gamma function of it. Okay? All right. So it is pretty interesting what you can extrapolate from that. Now, since this is a live show, if anyone is coming in, okay. Just 1 second, we're on page 2, were we? Yeah, page 2. Okay, let me see if anyone is coming in. Don't be shy. This is about making advanced math great again. Okay. All right. So we have to understand, right, how we're going to interpret this, right? So that, as I said before, we said gamma of n, but here is the improper integral of x to the n minus 1 e to the negative x dx. So we found the factorial, because remember, gamma function has to do with factorials. Here, though, I can take the gamma function of a complex type of number. Okay. So my question to you is, I won't do it. I want you to fill in the blanks for anyone who's coming in, okay? Because this is a live show, right? So fill in the blanks here, and if someone can tell me if I were to do this, right? If this is legitimate, if I can also say gamma of z, where z is a plus ib, right? A plus ib, okay? And this is also equal to the integral from 0 to infinity of x to the a plus ib, right? A plus ib, okay, on parentheses, minus 1 to the minus 1 power. So x all to the power of a plus ib minus 1 power times e to the negative x dx. Can I do anything with that? Can I prove? My question to you is, can I prove known theorems of known gamma function or gamma identity theorems if it's written in terms of a complex number? Can I do the same thing? In other words, my point is, right, with math, especially with definitions and theorems, more so than formulas, definitions and theorems, it can, if you read and understand the definition, sometimes you can extrapolate new knowledge, not all the time, but new questions from what is already known, okay? So quite often having the definition, if you understand the definition really well, you can extrapolate new information, new types of connections, actually, if you ask the right questions, right? So asking the right questions from a definition will help you really understand the material at a deep conceptual level, okay? That's what I want the audience to do, right? I want you to, it can really help, especially for advanced math, because advanced math, this goes off and it can get abstract, right? So having multiple questions can help clear any types of misconceptions in the theory, okay? All right, so let's move on. Definition 3, okay? We're going to look at a factorial generalization, all right? So any of you familiar, even if you're not, you know from earlier I was talking about the n factorials. That's what we're talking about right now, okay? So we were talking about the n factorials, all right? So we're looking at a factorial, definition 3, factorial generalization of the gamma function. So for any positive integer n, right, the gamma function, okay, so let's be precise, the gamma function satisfies gamma of n is equal to n minus 1 factorial. Is there any misunderstanding here with anybody? Okay, anything at all? Is there any type of misunderstanding in terms of the factorial generalization of the gamma function that I've highlighted right here? Please put thumbs up in the chat, or put in gamma for gamma function. I love the gamma function. It's my favorite integral practically, or one of my favorites. And I hope it will be your favorite too, for those of you who are watching. Okay. All right. So if not, I'll continue. Right. So satisfies gamma of n is equal to n minus 1 all factorial. Okay. So where n is an integer. So for example, if I wanted to calculate gamma of 1, right? Let's say n is 1. In other words, if n is 1, think of it as saying 1 factorial, right? If you compare gamma of 1 to 1 factorial, right? So at n is 1, gamma of 1 is equal to 1 minus 1 factorial. Okay. Now 1 minus 1 factorial is 0 factorial. 0 factorial is 1. So gamma of 1 is 1. And you can compare if this makes sense, right? Gamma of 1 is 1. Compare it with n factorial. Okay. Right. So n factorial when n is 1. So 1 factorial is just 1. So you can see both of these work. Okay. If there's any questions in the chat? Any questions? Not at the moment. Okay. So we're looking at gamma of 1, right? So I just shown to you that gamma of 1 is equal to 1. Okay. And it's the same thing as saying n factorial. Okay. So n factorial. Same thing as gamma of 1. Right. So let's say you want to calculate gamma of 3. Okay, so gamma of 3 now will be 3 minus 1 factorial, which is just 2 factorial, which is just 2. So gamma of 3 is 2, and so forth. Okay, so this helps us calculate the gamma function of integer values. Okay, now note, I always need to clarify this because quite often people say, what if you have a fractional value or a rational number? Does this definition formula work? No, it doesn't. Only works for positive integer values, not for rational numbers. Okay, so only positive integer values. There are other expressions that take care of other cases for the gamma function. All right. All right. So let's look at definition 4 if there's no question. All right. So definition 4. Definition 4. So if any of you have ever seen the recursion relationship, okay, so the recursion relationship, okay, so this has to do with a functional type of equation. You don't need to know what functional equations are, and my book does not go through functional equations, right? Neither do I. I don't think I even done any independent the functional equations. If you want to learn functional equations, I can always give you resources to functional equations. But yeah, it's not. It's just a phrase I put in because it's accurate. Because the gamma equation below is a functional equation. So a functional equation satisfies the following: gamma of z plus 1 is equal to z times gamma of z. Okay, so what does this mean? What does definition 4 mean? What does definition 4 mean? Anybody? What does definition 4 mean? I will wait for someone to come in and give me an answer. For the gamma function, right? So gamma of z plus 1 equals z gamma of z. What does this expression represent? What is it used for? The one that I have in the asterisk, what is this used for, if anybody knows? It is a gamma type of equation, but it's used for special cases. The expression is used only, I've written down here, only used for non-complex, right? So non-complex, that means not complex, integer values, okay? So that means it's not complex, can't be a complex number, okay? And it cannot be an integer number. That's why I said non-complex integer values. So that applies for the whole phrase, right? So that only leaves in rational numbers, like negative a half, 1/2, 3/2, so forth, okay? So this is the expression we would use if we have to deal with something like that, okay? So let's say, for instance, we want to calculate gamma of 3/2, okay? Gamma of 3/2. Does anyone know how we do that using the formula above? Gamma of z plus 1. Remember, gamma of z plus 1 is z gamma of z. Again, for those of you who are coming in, don't be shy, as long as you have a background in calculus, okay? In calculus 1 in university and linear algebra, you should be able to understand the content of these lectures. Okay. STEM Online Academy is here to help those of you who want to improve your mathematical maturity, whether you're a student who wants to, who's already in as an undergraduate. So clearly you've gotten somewhere, you've done something right. But you'll notice in university studies, you may still hit some sort of roadblock because your mathematical intuition hasn't been fully developed. So the questions and problems that I do and concepts, especially from my book and also in general that I teach, has to do with helping you develop this type of intuition in advanced mathematics. Okay. So for those of you who are out there that need tutoring, I'm always available. Okay, always available for new clients at STEM Online Academy. It will be in the link in the description below. All right, so back again, right? So the functional equation satisfies the following: gamma of z plus 1 is z gamma of z. Okay, so z gamma of z. Okay, so this expression, okay, the expression is used only for non-complex integer values, as I mentioned. That means only for rational values, positive, negative, yeah, rational values. Okay, so if we wanted to calculate gamma of 3/2, right? The way we do that, use the formula, gamma of z plus 1, okay? Z plus 1 is equal to z gamma of z, okay? Now here, don't get confused. Don't think that z is 3/2. Z is not 3/2. We're looking for gamma of 3/2, but since we're using the gamma of z plus 1 formula, is z 3/2? I already gave you the answer, but why is it not 3/2? Why is it not 3/2? Right, with z being, remember, looking for gamma of 3/2, we have to use the above formula here, gamma of z plus 1, okay, equals z gamma of z. But z is not 3/2 here. Z is 1/2, because the reason for that is because if z is 1/2, then 1/2 plus 1 gives you 3/2. Like so like the denominator and like terms and everything, common denominator, you'll get gamma of 3/2 is what we're looking for, right? That's why z has to be 1/2, because 1/2 plus 1 will give me 3/2, if that makes sense. Okay. However, on the right side, if z is 1/2, from our formula on the right hand side of the formula is gamma of z, z it has to be 1/2, so 1/2 times gamma of 1/2, if that makes sense. Okay. Should be pretty straightforward, right? But yeah, so z would have to be 1/2 in order for this to work, in order to get gamma of 3/2. Okay. All right. Let me see if anyone else is coming in. Okay, anyone else is coming in. So we're going to get gamma of 1/2 plus 1, right, is equal to 1/2 of gamma of 1/2. So gamma of 3/2, we're down here now. Okay. Put the asterisk in. That's where we're at. Gamma of 3/2 is going to be 1/2 of root pi. How do I know that? 1/2 of 1 is 1 to 3/2, so gamma of 3/2, right-hand side becomes 1/2 times whatever gamma of 1/2 is. And you should know what the gamma of 1/2 is. It's root pi. You can check it in a table, or you could have done the definition of the gamma function, the improper integral, check that x is 1/2, and then translate it into a Gaussian type of integral. Because it's a Gaussian integral e to negative x squared dx, and then you get that being root pi, and that substitutes for gamma of 1/2. Okay, so 1/2 times root pi. So gamma of 3/2 is root pi over 2. Okay, if that makes any sense. So gamma of 3/2 is root pi over 2. If there's any dispute on that, please let me know. Okay, so we've talked about that. So be any dispute. Okay, so we're off to, okay, so the next part here, yeah, I think that's the next part. Let me double check. Yeah, more or less. Before getting to that, let's talk about part 4, because we've done part 1 and 2 and 3 from today's menu. Okay, from today's mathematical menu, we have done part 1, part 2, and part 3. Yay! Let's make math great again, people. God. Anyone agree? Let's make math great again. All right, so part 4, graphing the integrand. And why is this important? Okay, so let's go back to the desktop. Okay. I'm going to stop sharing for now. Just give me a moment. Stop sharing. Okay. Then we're going to go and share my screen. Okay, and share the screen. Okay, so that's not it. Tell your screen. Chrome, where was it? Windows. Just give me a sec. I have to check something here. Something's not working. And hopefully you can see it. Okay, I'm going to share a screen. Just give me a moment. No, something I wanted to do. Share screen. Okay, yeah. Yes, Desmos. All right. Let me go to Desmos. If anyone can see what's going on, please let me know. Oh, hi, Gula. Hi. Golu Rajput, nice to meet you. I don't know if you've seen my other videos on advanced mathematics and physics. That's what this channel is, STEM Online Academy. Hope you like and subscribe. Okay. Tell me about yourself. Do you have an interest in mathematics? In high school, university, undergraduate? All right, so we'll continue with what I'm talking about until Gold gets back to me. All right, so as I said, we're going to graph the integrand of the gamma function. That's the x to the n minus 1 times e to the negative x product. Okay, now as you can see here, all right, is that we have a bit of a thing here. Okay, so just give me one moment. All right, so as you can see, the function right? The function looks very interesting, this product x to the n minus 1 e to the negative x. Okay, if we zoom in on the function, right, you can see that it behaves very asymptotically. Okay, you can see that the right end, the red curve, right, on the right end here, okay, pretty much has a asymptote. Okay, so the right curve here, right, as you go up, right, like this, it's asymptotic to the y-axis. Okay, and the asymptote, can anyone tell me what the asymptote is? This is a review of like grade 11 math, I believe. What's the asymptote, if anyone in the audience is interested in knowing the asymptote? What's the asymptote? Come on, guys. What is the asymptote of this function, the red curve that is approaching the y-axis? X is 0, right? X is 0 is one of the a vertical asymptote. That's one of the vertical asymptotes. Okay, that should be straightforward, right? So that's one of the asymptotes. Another asymptote, if anyone can tell me, what's the other asymptote, vertical asymptote in this graph here? If anyone knows, this is good practice for those of you who want to refresh your grade 11, 12 algebra. What's the vertical asymptote? What's the other vertical asymptote besides x equals 0? Looks like it's at x equals negative 10, from what I can see here, right? At x equals negative 10, right? The curve down here, right? Is it negative 10? Oh, wait, sorry. No, it's not negative 10. No, because it crosses negative 10. That can't be an asymptote. It doesn't look asymptotic on the left branch of the lower curve here, as you can see. From a geometric perspective, it doesn't look like it. Anyone have any thoughts on the other asymptote? If there is another asymptote. Right, so we're looking at the graph of the gamma function, right? X to the n minus 1, e to the negative x, where n is a slider or some changing variable. Okay. So let's go ahead and play the slider. This is on Desmos, by the way, so you should know what Desmos is. It's graphing software. So let's do it. So can anyone tell me this interesting behavior of the function? Anyone tell me the interesting behavior here? So what's going on with the function here? What's going on, right? So let's say I change my my parameters from negative 1 to 2. Let's say there's no step. Step is nothing. Let's say, for instance, something interesting happens. So the curve really spirals out of control. But it looks like, as I said, we can agree that there is a vertical asymptote at y equals 0, right? X equals 0, sorry. And if there's another vertical, is there any other vertical or horizontal asymptotes that we know about this graph here? Yes, you can. Yes. Can you, in math, can you ever have a horizontal asymptote? Yes. Yeah, of course. Yeah, a horizontal asymptote would appear in multiple cases. For instance, let's say you had, just give me a sec here. If you had y equals 1 over x, right? There's vertical and horizontal asymptotes, right? Okay, so let's get out of this for a sec. Yeah, so I might get out of, let me stop sharing. Just give me a moment. Let's see, stop share. And then I'll go to my share screen. Okay, so let's go over here. So let's go to the entire screen, go to the whiteboard. Just give me a moment, I'm going to explain. Okay. All right, so if you look at a graph here, right? Okay, so I'll give you the graph here, right? y equals 1 over x, right? Looks like this. Okay, so let's say you had x, y, 1 over x behaves like this. Okay, you can see that it's a vertical and horizontal asymptote. That's not exactly accurate at the bottom, but I hope you get the point. This is not supposed to be touching the y-axis. That's why it's a asymptote. Okay, but there's a vertical asymptote here at x equals 0, and then there's a horizontal asymptote because the graph is approaching the x-axis. It never hits the x-axis, if that makes sense. You know what I mean? Okay, so at y equals 0, right? There's an asymptote as well. Okay, I hope that answers your question. Matthew Battiston. All right. Now, for trig functions, very good question. Yeah. No, there shouldn't be a horizontal asymptote for the trig functions, right? So if you had, as you can see, right, sine, cos, and tan are all vertical well, sine and cos don't have any asymptotes. Tangent has vertical asymptotes. Cotangent, cosecant, if I'm remembering, cotangent, cosecant, and secant. Secant 1 over cosine, where x is equal to 0. Shouldn't be vertical. Oh wait, no, yes. I'm being silly. There is the horizontal asymptotes. For instance, if you have a trigonometric function like this, okay. So let's say you have something like secant, cosecant, or cotangent, right? You have vertical asymptotes, right, for the functions. But you can also have horizontal asymptotes as well, right? So you can have a graph like this for cosecant, secant, or cotangent, depending on what it is. One of them looks like this. Okay. Another one's like this. I forget how it is. It's not accurately drawn. I haven't done it as well, but okay. This here already constitutes as a horizontal asymptote. All right. So the inverse, I don't want to say inverse trig. I want to say like 1 over secant, 1 over cot. So y equals 1 over secant x, y equals 1 over cotangent x, and y equals 1. I should be saying that. Y equals cosecant, y equals cotangent. My mistake. Being silly. Cosecant x, cotangent x, and secant x. The graphs are similar to the one I've drawn. I'm not going to draw all of them, but forget which one this is for. But yeah, they do have horizontal asymptotes. Okay. So yes, trig functions can have horizontal asymptotes. Okay. Just not sine, cos, and tan. They shouldn't have it. Okay, perfect. I hope that explains it. By the way, Matthew, are you in high school or are you undergraduate at university? I'm just curious. Grade 12, nice. Okay. And yes, that's excellent. Good. Well, I hope you have an interest in learning some university level math. Okay. I don't know if you've taken calculus of any sort, but that's what this mainly is. All right. It's very good preparation for later mathematics. Okay. All right. So stay tuned. We're going to talk about some interesting concepts. All right. So where were we again? So we were talking about some things from a book. Last thing we were talking about was graphing the integrand x to the z minus 1 e to the negative x. Okay. I was talking about the behavior of the gamma function x to the z minus 1 e to the negative x. All right. And we're going to, I just wanted to mention, just bring back some high school stuff about vertical asymptotes, horizontal asymptotes, and stuff like that. But yes. Okay. So we've talked about this guy right here. Okay. Right, so talk about 4 things. The next thing we're going to talk about is the half integer miracle. And that is why The gamma of 1/2 is equal to root pi. Okay, so why is gamma of 1/2? Oh, perfect. Nice. Okay, so you're Canadian then, like me. Yeah, because I can tell by the course I used to back in the old days. Yeah, it was. Yeah, when I was a student, that was a long time ago. Yes. By the way, if you need help with that, course, I'm always available for tutoring. Okay. You can always check out in the chat. It will be over here, www.stemonline.com. We are a math and physics tutoring company. So if you ever need help, this is the place to go. Come. Okay. Over 5 years of experience in advanced tutoring. Oh, you're very welcome. You're very welcome. We'll keep in touch in that respect, right? But I hope you enjoyed the rest of the video. All right. So continuing, the half integer miracle, right? So gamma of 1/2 is equal to root pi. Okay. Now, as I said, I won't go into number 5 right away. I may need to reiterate the definitions of the gamma function because some people are coming in. Otherwise, they won't know what I'm talking about. Okay. So where was I? Let me go back here. So what is the gamma function? That's what I was talking about. Okay. So a gamma function is denoted as gamma of z. It's this Greek letter gamma of z. Okay. And it is a mathematical function that extends the concept of a factorial, okay, to complex and real numbers. Okay. For those of you who know what the factorial is, n factorial is n minus n times n minus 1 times n minus 2, so forth, right? If you've taken, data management, probability, or statistics, you will be familiar with what a factorial is, right? Anyone understand what I mean by factorials? Please do. I hope you understand what factorials are. Factorials are very handy. Yes, very handy. Okay. So yes, what a factorial is. So I'm just going to put that down again. So n factorial is equal to n times n minus 1 times n minus 2 dot n minus r plus 1. Okay. So if I were to find, let's say, 3 factorial, for those of you who don't know, that would have been 3, because n is 3. 3 times 3 minus 1 times 3 minus 2, and so forth, right? 3 factorial comes out to be 6 if you calculate it. All right. So that is what a gamma function is related to the factorial function. Okay. Now into more detailed definition too. Now I know the audience coming in hasn't seen what an integral is yet, unfortunately. Okay. So this might be a little bit advanced. Okay. But when you've seen calculus, when you do calculus, you're going to learn about derivatives. That's after advanced functions. After advanced functions is elementary differential calculus, right? And they just talk about, finding derivatives and limits. That's what it's about, okay? Finding slope of tangent lines. An example of this definition of an integration is the opposite of what a derivative is. It's finding the area under any type of curved shape. Okay, so this squiggly S that I have here, that's in this definition that I've highlighted, that's just what an integral is. Okay. All right. So we're going to be talking about what this is. Okay. So that's just some background. I'm sorry if I haven't given you all the background for integration for anyone who is, not having that mathematical maturity yet. But yes, I have to get into it. So the primary definition of the gamma function for a complex number z with a real and positive part, where the real part of z has to be strictly greater than 0. Complex numbers have real and imaginary parts. That's why I've highlighted over here. A complex number z is always written in terms of a plus ib. Okay, so a is the real part. That means just a regular number, right? So minus, let's say, from minus infinity to infinity on the real numbers. Okay, all of you understand what real numbers are. B being in the complex numbers. So what I mean by complex, I, 2i, 3i, so forth. Okay. Okay, so that's what a complex number is, a mixture of real and imaginary. Okay, the real part always has to be greater than 0 by this definition. Okay, always has to be greater than 0. All right, and it's an Euler type of integral of the second kind. Okay, so what I mean by that is that I'm highlighting over here, right? Putting a green asterisk. Gamma of z is equal to the integral from 0 to infinity of x to the z minus 1 e to the negative x dx. Okay, where z is a complex number. So this Euler type of integral applies to complex numbers and also real or fractional values as well, rational values. So complex, real, or rational values. Okay. All right, so that's definition 2. Now, definition 3. You want to make sure everyone's understanding, if not understanding, at least enjoying the content. Okay. So definition 3 now is a factorial generalization. Now, even if you don't have any experience with what I said above, you'll understand what definition 3 is, even if you haven't seen it before. So for any positive integer n, the gamma function satisfies this formula as well. Gamma of n is equal to n minus 1 factorial. Very basic formula, right? So if you were to calculate, so what do I mean by integer? Integer means a whole number, right? Okay. But it needs to be a positive whole integer. Can't be negative in order to use this formula. Gamma of n is n minus 1 factorial. So if we wanted to calculate gamma of 1, that would have been, well, n is 1, so 1 minus 1 factorial. 1 minus 1 is 0. 0 factorial is 1. Okay, if that makes sense to people. Hope it does. Right. Always put a thumbs up in the chat. I appreciate it. Or anything else. All right, so gamma of n is n minus 1 factorial. For instance, if you want to calculate gamma of 3, that would have been 3 minus 1 factorial, which is 2 factorial 2. Right? 2 factorial would have been 2 because 2 times 1. Remember, it's always n factorial is equal to n by n minus 1, and then so forth, right? So since it's 2 factorial, n is 2, 2 times 2 minus 1, and then so forth, 2 by 1 is 2. Okay? All right. Hopefully that's making sense for people. Okay, so we have that. Then we've got definition 4, the recursion relation. So this is a functional equation that satisfies the following. Gamma of z plus 1, in parentheses, is equal to z gamma of z. Okay. Now, this expression is used only in certain cases when you have non-complex integer values. Let me repeat. Non-complex integer values. That means when I don't have a complex number, right, and or an integer value. Okay, so it can't be for whole. It doesn't work for, well, it's not usually used for whole numbers, right? So integer values. That's not what it's used for. It's not used for complex numbers either. It's used for rational values. What I mean is fractions: 1/2, 3/2, 5/2, doesn't matter, 4/5. That's what gamma of z plus 1 equals z of gamma of z. If you want to calculate fractional factorials, that's what this would be. Okay. By the way, for those of you who are interested in taking statistics down the road as a career or anything of that nature, or you're in your university and you're taking statistics, this will be very handy. Gamma functions and Gaussian integrals is like your bread and butter. Well, I wouldn't say bread and butter, but up there in terms of importance. Okay. Yeah, it's very important for statistics. Okay, so non-complex integer values, right? So what would I mean? Example, if we want to calculate gamma of 3/2, as I'm pointing out here. Any questions? You have questions, let me know. I have to go back and forth in the chat. Can't see it on my whiteboard. Okay, so nothing yet. So gamma of 3/2. Okay, so if we want to calculate gamma of 3/2, all right, all we do is use the formula gamma of z plus 1 equals z gamma of z. Okay, and the reason for that is because we're dealing with fractional values. Okay, so I use gamma of z plus 1. Okay, so gamma of z plus 1 is equal to z gamma of z. Okay, Now here, we have to be careful. We're looking for gamma of 3/2. Z is not 3/2. Okay? If anyone can tell me why I said that, why Z is not 3/2, even though we're using gamma of Z plus 1 formula. Anyone at all? It's because we're looking for gamma of 3/2. So we need to find a Z such that when we add Z plus 1 gives us 3/2. So that Z has to be 1/2. 1/2 plus 1 gives you 3/2. So gamma of 1/2 plus 1 will give me gamma of 3/2. And then gamma of 3/2 will equal to 1/2 of gamma of 1/2, because gamma of 1/2 plus 1 is equal to 1/2 of gamma of 1/2. Which is this part of the formula. Makes sense? Hopefully the audience is following. Okay, that's why I did that. So it gives gamma of 1/2 plus 1 is 1/2 of gamma of 1/2. Okay, now we're on to step 3. Gamma of 3/2 is equal to 1/2 times root pi. Okay, now this will be somewhat, this is going to be pretty this is not trivial. It's a non-trivial approach. Like, how do I know the gamma of 1/2 is root pi? Okay, you can look it up in tables. Okay, if you look at gamma values of 1/2, for those of you who don't know and don't have any background in multivariable calculus, you're going to say, how on earth can I verify the gamma of 1/2 is root pi? You have to use tables. So you look at a gamma function table or a bell curve table. Calculate gamma of 1/2 will tell you that it's root pi. Okay, I can guarantee it. You can look up on the internet right now, ask what gamma of 1/2 is. It's root pi. Okay, so then we get 1/2 times root pi. Okay, so you get root pi over 2. So gamma of 3/2 is equal to root pi over 2. Okay, so it's pretty interesting stuff. Any questions on these definitions and theorems of the gamma function? Okay, nothing yet. Let's move on. All right, so we've already done halfway through, right? Talked about the gamma function, y gamma of n equals n minus 1 factorial, why I did the Desmos graphing of x to the z minus 1 of e to the negative x, the asymptotes of the gamma function, right? That's what it was. And then the half integer miracle, I like to call it, gamma of 1/2 is root pi. Now we're going to move to part 6. This is the Gaussian integral and pi connection. I think we're going to talk about. Okay, part 6. Or, you know what? I was thinking we may do a verification of something here. Yeah, I'm going to do a verification. We may want to prove why gamma of z plus 1 is equal to z gamma of z. Yeah, let's do that. Okay. So given the definitions I've talked about for the gamma function, okay, so I talked about the gamma function, gamma of z, what it is, definition 1, like what it means, like semantically what it means anyways in language terms. So definition 1. Definition 2, the primary definition of the gamma function for complex numbers, z in real positive parts, where the real part has to be greater than 0 for the other integral of the second kind. There's always the improper integral of x to the z minus 1 e to the negative x dx. Okay, so it's an integral that you can integrate, right? Definition 3, the factorial generalization, right? We talked about that as well. Gamma of n is equal to n minus 1 factorial, right? And finally, definition 4, the recursion relation. Gamma of z plus 1 is z gamma of z. This is only used for non-complex integer values, okay? Where the factorial generalizations is used for positive integer values. Okay, so make sure you're able to distinguish those. However, now this is where your calculus skills may come in handy. Okay, so if anyone has any background in calculus, let's say 1 or 2, definitely by 2, calculus 2, you should have it. Or you've taken IB calculus. If you've taken out IB calculus, that can be handy as well, because when you do integration, hint, hint, integration by parts will help you solve this problem. Anyone want to take a go at it? Anybody in the chat want to tackle this cool problem? Anybody? If not, I'm going to show you how to deal with this. Okay. So please let me know. Anyone have any ideas of how to approach this? You know what the definition of a gamma function is in terms of z, right? It's this guy over here. Anyone want to take a go? Okay, so I'm going to do it. Yes, it looks a little daunting, but we can get through it. So the way to prove this, right? So I'm going to talk about proving this. Okay, so let's prove the following. So prove, I'm going to say the proof here. Proofs, for those of you who don't know or do know, act like trigonometric identities. Okay, so for those of you who have done trigonometric identities, when you do university math, at least depends what program you're in. If you're going into math, physics, or engineering, quite often the proofs will be very important. If you're not in that stream of math, physics, or engineering, but you go to university, you won't be responsible for proofs. Okay. Outside of STEM, it won't be as important. But yeah, in the hardcore STEM subjects, it's all proofs, especially if you go into pure math, it's all proofs. There's no calculations whatsoever. But the point is, it's very handy to be able to prove things. Okay. All right. So the way we do it, we want to make sure that the left-hand side equals the right-hand side, if anyone understands what I mean. Okay. That's all we're doing when we're proving this. Okay. So what I'm going to do is I'm going to so since we know that, I'm going to say it's already, so I'm going to write something here. Okay. So say it's already defined. Already defined. It's already defined that the gamma function, right? So the gamma function of z is equal to the integral from 0 to infinity. It's an improper integral, x to the z minus 1, e to the negative x dx. Okay, so this guy here, obviously I'm going to use that because I have to do some manipulations with this expression. Okay, so gamma of z is equal to this improper integral. Okay, that's gamma of z. Now, then I'm going to say, then I can say something of gamma. Actually, I'm going to make some room here. Yeah, I'm going to make some room. Gamma of z plus 1. So I'm going to say something about gamma of z plus 1. Obviously, I need gamma expression for gamma of z plus 1 because that's the left-hand side of the equation, right? So that's what I'm doing. I'm rewriting the top integral. It now becomes the integral from 0 to infinity of x to the... Now, remember, for every z, I'm replacing z plus 1. So what goes in the exponent? Z plus 1, right? Every z gets represented with z plus 1. And then, so z is replaced with z plus 1, then minus 1. And then it's e to the negative x dx, if that makes sense, okay? Okay, so now we have this. So then we can clean this up. We can say that this is now the gamma function of z plus 1, and this is equal to the integral from 0 to infinity of x. 1 minus 1 is gone. That's left x to the z times e to the negative x dx. Okay. So I have this integral now. That's a bit annoying. If anyone have any integral calculus knowledge and wants to take that on? Anybody at all know how to integrate x to the z, e to the negative x specifically? Yes, it does look intimidating, but it's not that bad as long as you have a background in integral calculus. Anyone can do it. Even if you've never seen a gamma function before and you take an integral calculus, you can integrate this problem. Anybody in the chat? Okay, so it looks like I'm going to have to do it. So the way you do it is you're going to sit, anytime you have a product of two functions, here we have x to the z and we have e to the negative x multiplied by each other. Not all the time, but most of the time, you want to use something called integration by parts. And that is split up like this. You have one part is your u, the other part is your dv. Your dv is your differential or your derivative part. Okay. And quite often, we want to know what our u and our dv is. I'm going to say let u, okay, so let u equal x to the z, okay, let du, now my differential, what I mean by the differential, I have to find du as well. So if I have u, I need to find du. If I have dv, I have to find v, okay? Automatically, we start with u dv when we're using integration by parts. Okay, so u equals x to the z, du is equal to z times x to the z minus 1 with respect to x, power rule of derivatives, right, for differential calculus, right? X is the variable, z is a constant. Constant goes in front, right? Z by x to the z minus 1 dx, if that makes sense. So everyone's following along here. Okay, so that's what we have. All right, the next part is the dv. Okay, so what is dv? dv is just e to the negative x dx, right? That's this part here that's highlighted. By the way, your differential is always with respect to the variable. So in this case, x that we're integrating, right? And then after here, v is going to be the integral of e to the negative x. That's just minus e to the negative x, okay? All right, so we have our u, we have our du, we have our dv, we have our v. Okay, then what we want to use is the integration by parts formula, right? So the definition, right? So it's just this. It's the integral of u dv is equal to the product of u times v minus the integral of v du. That's like an integral of v du. Okay. I have too many things on my chair here. Sorry about that. Damn it. Oh, come on. Sometimes it feels like Kevin. I really should put a hanger from this shirt here. I'm sure you can agree. Okay, so so we have this integration by parts formula here. Okay, so that's what we want to use. So we have everything that we need now. Now, I'm going to say that, so integral of u dv, we know what it was, x to the z, integral of x to the z, e to the negative x dx. That's what we're finding. So integral 0 to infinity of x to the z minus 1, e to the negative x dx. Okay. And this is automatically equal, right? This is automatically equal to u times v, right? So minus x to the z, e to the negative x from 0 to infinity. Okay. Actually, I'm going to do this instead. It's better since we don't want to say equals infinity. Nothing equals infinity, just approaches infinity, right? We want to put a limit sign. It's better to put a limit. I'm going to say limit of a dummy variable t. T approaches infinity of u times v. U times v was x to the z. Yeah, x to the z. X to the z minus x to the z, because you had minus e to the negative x here, minus x to the z, e to the negative x. Negative x. Limits of integration are from 0 to t, where t was approaching infinity. Okay, because our integral is going from 0 to infinity on the left-hand side here. Okay, so 0 to t minus the integral from 0 to t, replacing the infinity with t's now. V du. V was minus e to the negative x, so times the negative e to the negative x. Du is multiplied by z times x to the z minus 1 with respect to x, bracket, another bracket. No, it's to be a square bracket, but you get the idea. Okay. Any questions in the chat? All right. So if not, we'll continue. And I'll continue writing. So limit as t approaches infinity, on square brackets, this is minus x to the z, e to the negative x from 0 to t. Okay, 0 to t. And then negative times negative is positive, so this becomes positive. Z is a constant that can be brought out front. This is just the integral from 0 to t of e to the negative x times x to the z minus 1 dx, all in square brackets. Okay. So this is what we have right now. Now, some of you may notice something. Some of you may notice something. This integral here, or the next step, is the definition of something. What's it the definition of? What is that integral the definition of? Integral from 0 to t of e to the negative x, x to the z minus 1 dx. What type of integral is this? Anyone know? It's a gamma integral, right? Remember what I said earlier, that gamma of z is equal to the integral from 0 to infinity of x to the z minus 1 e to the negative x dx. Here we have integral e to the negative x, x to the z minus 1 dx. It's the same thing as saying x to the z minus 1 e to the negative x dx. So this portion here can be replaced with gamma of z. You understand? So that's to be gamma of z here. So I can rewrite my expression like this now. Limit as t approaches infinity, square brackets, minus x to the z times e to the negative x. Limits of integration go from 0 to t plus z gamma of z, because this is gamma of z. Does that make sense? Okay, so this is what we've got right now. Okay, and this is just the limit as t approaches infinity. We have all in square brackets, minus x to the z, e to the negative x, 0 to t. Now, I can put my limits of integration, actually. I'm going to plug in my limits of integration. So since we have an upper and lower limit, remember what we're supposed to do. We're supposed to do whatever this function is, the upper limit minus what the function is minus the lower limit, right? So it's like f of b, where this is my b, and this is my a. So f of b, this is the function, right? This is the antiderivative function, f of x, let's say. And then f of b, the upper limit minus the lower limit. So it's going to be minus, in this case, my b is t. So minus t squared e to the negative t. Okay, so minus t squared e to the negative t. Right, that's the upper limit. Now we do the lower limit, the lower bound here at 0. So minus, next we subtract. That's part of the formula f of b minus f of a, but since we have negatives, negative of 0 squared e to the 0, okay, like this, plus z times gamma of z. Hopefully everyone's following. Okay. Don't forget to put something in the chat, like and subscribe. Hopefully you're enjoying the video, the live video. Yeah, I appreciate the kind words anyone can put in the chat. Okay, so we're continuing, right? So we have limit as t is going to infinity. Now this becomes easy, right? 0 times anything, this is gone. I'm left with the minus t squared, right? So minus t squared e to the negative t plus z gamma of z. Okay. However, though, we're approaching t approaches infinity. That's not going to affect the z gamma of z. Okay, z gamma of z is independent of t. Nothing's happening to it with a limit. However, something's happening with this t squared e to the negative t. If t approaches infinity, okay, t squared e to the negative t, what is it approaching if t approaches infinity? For those of you who have some simple calculus backgrounds, know this. T squared e to the negative t. T is approaching infinity. So what happens to the product of t squared e to the negative t? Anybody know? Anyone knows what happens if t squared e to the negative t? First off, we know, this is why I always emphasize, whether it's the most abstract math or the most simple math, is to always make diagrams, because this is another proof why my unique perspective always works. Okay, so e to the negative t, you should know how that looks like. That's a decaying function, exponential decay. Okay, so it looks something like this. It's not exact, but you get the idea. Okay, now as t is approaching infinity, right? Infinity is the positive x-axis. It's going like here, right? Positive infinity. So I'm going to write here as t approaches positive infinity, then t squared, right? E to the negative t approaches 0. It has to, because this portion here on the x-axis, we know that e to the negative t has a horizontal asymptote, correct? It should be a horizontal asymptote there, right? So since there's a horizontal asymptote, it's approaching 0. If it's approaching 0, this is 0. Okay, so I'm just left with z gamma of z, right? And the limit as t approaches infinity of z gamma of z doesn't do anything. Limit of a variable, or well, a variable that's acting as a constant, because there's no t in here, is this the constant, so z gamma of z. Oh, and look, we've proved it. The left-hand side, right, this guy here, okay, that was z. Yeah, this was, yeah, we were finding z, not z minus 1. This guy here was just gamma of z plus 1. That's why we got that x to the z here, right? Gamma of z plus 1. We want to verify that gamma of z plus 1 is equal to z gamma of z, and we just did, right? The right-hand side is a gamma of z. The left hand is gamma of z plus 1. So therefore, I'm going to say thus gamma of z plus 1 is equal to z times the gamma of z. And we've proven it. Any questions? Okay. So that's how we verified that part right there. Okay, so we verified one of the gamma identities. So let's see where we're at here. Another thing. So we didn't do 5 yet. Okay, so we want to show that gamma of 1/2 is root pi. Okay, so gamma of 1/2 is root pi. Why is that? Let us go and do that. Okay, so let's see here. Yeah. So we talked about that. Next thing we want to do. Did I make room here? Let me see. Yeah. No. Do I have room? No, I don't. Oh, damn it. Did I make room? I don't think I made room. That's okay. I'll use the other part here. The other side of the blackboard. Okay. So we're now going to talk about calculating gamma of 1/2 y is root pi. Right. So we're going to prove. So now we're going to prove this. We're going to prove that gamma of 1/2 is equal to root pi. Okay. I like to make my pies better. second root. Okay, so here's the proof. Let's make sure anyone else is coming in. Anyone else coming in here? So make sure we've got 5 people. Put thumbs up, guys. Put thumbs up will be appreciated. Okay, so proof. We want to prove that gamma of 1/2 is equal to root pi. Okay, the way to do that, right, is again, we start by the integral definition of the gamma function. Okay, the gamma function is the following, right? It is defined, I'll say DEFN, right? That's gamma, I'll just say gamma of n, doesn't matter. Gamma of n is equal to the improper integral 0 to infinity of x, 1 second here, x to the n minus 1, x to the n minus 1 times e to the negative x dx, right? This is, I'm just stating, this is the definition, DEFN for definition of the gamma function. Gamma function, okay? Right, so that's what we have. Now, we want to find gamma of 1/2, right? So let's plug that into our formula here. So gamma of 1/2, when n is 1/2, is equal to, that's going to be an infinity, by the way. I like to make my infinities, come on. Where's my infinity? So integral, right? So integral from 0 to infinity of x to the n is 1/2, power of 1/2 minus 1, e to the negative x dx. That's the integral we're calculating. Okay. Now, from this step, gamma of 1/2 is the integral, improper integral of the simplified form, x to the negative 1/2, e to the negative x dx. So we need to use an integration method. What integration method should we use? What integration method should we use here to integrate this? Yes, I'm asking the audience. What integration method do I need to use in order to integrate x to the negative 1/2 e to the negative x dx? And it turns out, be careful, we don't need to use the integration by parts like last time. If you use integration by parts, you'll make it more complicated for yourself. Let's just say it that way. I'm not saying it's not possible, but it just makes it more, maybe a bit more annoying. Just use direct U substitution. Okay. Quite often when integrating, for those of you who don't know or have some background with integral calculus, is that you have to be able to notice intuitively when to use what integral method when it comes to calculus. Okay, it's not always obvious, but there are some tricks. Here, you will have to notice that my u, right? Okay, my u, so if I let, so I'm going to use u substitution, right? So I'm going to put here, let u, right? So let u equal, let's see here, let u squared equal x. Okay, I'm going to explain after why this works. U squared is equal to x. Okay, the next thing I'm going to do is that I'm going to, if u squared is equal to x, if I solve for u is equal to x to the 1/2. Okay, that's one thing. I'm actually going to put it over here, actually. I'm going to say that, yeah, so this implies, yeah, that's fine. U is equal to x to the 1/2. Anyone have any questions on that? why is u equal to x to the 1/2? Well, I solved for u. So u is equal to x to the 1/2 of the square, right? However, how did I know to take u squared? That's going to come in a second. Now, another thing too, if we have u and we're using u substitution on an integral, we need to figure out its differential, the du. So du now on the original u is going to be equal to 2u, right? So 2u, sorry, I made a mistake there. That u squared, which is equal to x, should be 2u du equals dx. Okay? Right? Here's the reason why. Here's the reason why I chose u squared equal to x. If I let u squared equal x, there's two reasons. First off, if I substitute, I want to make sure when I use u substitution, all of my x's are replaced with u's. Okay, that like use the new parameter in the function. Everything's a function of u. Okay, that's the first reason. Second reason is having u squared equal to x, that means I can replace this with e to the negative u squared. Okay. And then if I have e to the negative u squared, okay, then I can, well, the fact that I have x in terms of u squared, that helps. But the fact that I have u squared equal to x, and I need to find my du by differentiating both sides with respect to each variable, du and dx, this becomes 2u du by power rule. The right-hand side is dx. Okay. By having it like this, I take care of replacing my dx. In other words, I have the correct function u such that when I differentiate u and get my differential in terms of u, I replace my dx and I replace all of my x's without having any problems, if that makes sense. Okay, so that's the reason why I chose this. Okay, so let's substitute this in. So this is now integral from 0 to infinity. Okay, 0 to infinity. Okay, of x to the negative half. Now remember what my x is. X is u squared. This becomes u squared to the negative 1/2. See how I'm replacing everything in terms of u? Just 1 second here. Okay, then this is times e, right? So as I mentioned, I replace everything in terms of u. E to the negative x, x is u squared, so negative u squared. Dx is now going to be times 2u du. Hope that makes sense. So that's what u substitution is. You want to make everything in terms of u. Okay. Then from here, this integral from 0 to infinity, u to the power of 2 times negative 1/2 is u to the negative 1 times e to the negative u squared times 2u du. Okay. All right. Hope you guys are enjoying. It gets really cool, actually. All right, so this is what we have now. Now, the 2, every constant goes in front of the interval. So I can say 2 times integral from 0 to infinity, u to the negative 1 times u, right? Just move this to the front. U negative 1 times u times e to the negative u squared du. U to the negative 1 times u cancels, because that's like saying 1 over u times u. U divided by u is gone. So I'm left with twice integral from 0 to infinity of e to the negative u squared du. Okay, so that's what I have now. Now this says twice the integral from 0 to infinity. So this automatically means that this is equivalent to the improper integral from minus infinity to infinity of e to the negative u squared du. This is an integral property that I'm using. Right? Twice the integral from 0 to infinity is automatically, by definition of an integral property, is the integral from minus infinity to infinity. Right? And there's a reason why I wanted to write it like this as opposed to having the 2 times the integral 0 to infinity. It's a Gaussian integral. That is the reason. Okay? It's a Gaussian integral. All right? Those of you who enjoy Gaussian integrals, have any multivariable calculus, you'll know what I'm doing, right? So you'll know that this automatically is equal, right, to root pi. Okay, automatically this has to be equal to root pi. I'm not going to verify this here. If you want to look at the verification, I have another video on the gamma function that I talk about the pure derivation of it using polar coordinate transformations and double intervals. Okay, so this is automatically. I'm just going to say this is by the definition. The justification here is the definition of the Gaussian integral. Definition of Gaussian integral. Okay, and since that's equal to root pi, and this entire integral was equal originally to gamma of 1/2, we verify gamma of 1/2 is equal to root pi. Okay, so yay, right? So gamma of 1/2 is root pi. We've verified that. Okay, that's gone. Gaussian integral pi connection. I was pretty much talking about that. 5 and 6 are both done, because if you pretty much have, you verify that it's root pi, I explained why, right? The Gaussian integral, you can look up the definition, is automatically equal to root pi, right? It's not just in my book that I'm using from the problems, the definition of my book. It's a fact, it's a definition in general that the integral from -∞ to infinity of e to the negative u squared du is root pi. Okay. All right. So, anyone have questions? Okay, nothing yet. Okay, so we've talked about, let's see what we've talked about here. Let's go back. Okay, so we've talked about Gaussian integral product connection. Let's talk about the reflection formula, gamma of z times gamma of 1 minus z. That's another type of formula that comes up with the gamma function. Okay, so let's talk about that. So we're going to talk about asymptotics and Stirling's approximate. Oh, what am I doing? Not Stirling yet. Where are we? Damn it. What are we talking about? Yeah, we're talking about the gamma of z. Gamma of 1 minus z. 1 second. Do I have it here? I wanted to talk about it. I think it was over. We've talked about that. Yeah. Yeah, I talked about that. Is it again? 1 minus z. Where is it? That's weird. Okay, that's weird. I wanted to talk about it. Let me see. The gamma of z times gamma of 1 minus z, all you need to know is that it's a product of two gamma functions as a function of z times z minus 1, and that z cannot be plus or minus 1, plus or minus 2, plus or minus 3 in that formula. Okay. I don't know why I wrote this down way before starting. There's quite a few stuff, but let me see if I can find it. No, I can't. Oh, there it is. Yes. The reflection formula, gamma of z times gamma of 1 minus z is pi over sine pi z. Okay, so this is another gamma function identity I want to talk about. I mentioned the other ones, but this one, we're going to get into it. So important points is that the domain, the formula is valid for all complex numbers z, except at these guys here. These are practically restrictions on the domain. Z being 0, Z being plus or minus 1, plus or minus 2, plus or minus 3, so forth. Okay. So that's with respect to the domain. Okay. So in other words, the non-positive integers are the poles of the gamma function. Let me repeat. The non-positive integers are the poles of the gamma function. Okay. So those are the poles of the gamma function. While at positive integers, the sine function is 0. Think about it. The reflection formula right here, gamma of z of gamma of 1 minus z is equal to pi over sine pi z. If z is an integer value, it will just be sine times n pi. N is some integer. So any integer of where n is an integer times pi will give you, 0. Sine pi is 0. Sine 2 pi is 0. Sine 3 pi is 0. Right? That's what I mean. Okay, so that's one of the important points of the reflection formula. Okay. Now, another thing I want to mention too, the connection to other functions. This formula establishes a deep connection between the gamma function and the sine function, as you can see, right? Anyone have questions on that specific formula? Not that I can see so far. And you guys have. Okay, so it's just an interesting fact that the sine function is related to the gamma function in this sense, right? So gamma of z, gamma of a complex number times gamma of 1 minus a complex number, is equal to pi divided by sine pi z. Okay. And in terms of the applications, it's very useful for calculating values of the gamma function. So non-integer. So here's the thing. The other gamma identities I talked about were for different cases. You use each one for a specific case. This one now is for non-integer, careful here, non-integer and negative values. So non-integer means not a whole value, so fractional values, right? So 1/2, 3/2, and so forth. This equation can calculate it as well. Okay, this guy up here can calculate non-integer values. Okay, and for negative values, it can calculate negative values as well. Okay, so non-integer and negative values. Let's say we want to calculate gamma of 1/2. Okay, let's do that. If there's any questions, just checking the chat. No. Okay, so if you want to calculate gamma of 1/2, this would be gamma of gamma z, gamma 1 minus z, pi over sine pi z. The reflection formula, right? We use gamma of 1/2 times gamma of 1 minus 1/2 pi divided by sine pi times 1/2. Okay, very straightforward. The left-hand side is now gamma of 1/2, gamma of 1/2. That's pi over sine pi over 2. Okay. All right. And then from here, gamma of 1/2 all squared, because it's gamma of 1/2 times gamma of 1/2. Okay, so gamma of 1/2 all squared now is equal to pi, because pi divided by sine pi over 2, sine pi over 2 is 1, right, by the special angles in the unit circle. So pi over 1 is pi. Therefore, if I solve for gamma of 1/2, I have to square root both sides. Gamma of 1/2 is root pi. So this is another way to verify and actually calculate fractional values. And you can see once again, it proves once again gamma of 1/2 is root pi. Okay. Now, for those of you who have or are in, I don't know, this is mainly for undergraduates in university, but those of you who are in the chat who are taking or are going to take something called data management and probability or statistics, this relationship is very important, and it comes up in something called a probability density function. Okay. If any of you know what a probability density function is. Okay. So what I mean is something that has a bell curve, if you understand what I mean, right? So any bell curve like this. Okay, so let's say we have something drawing a graph here, which is the center points here being the mean, okay, and moving away certain standard deviations away from the mean, right? This would be positive sigma. This would be negative, like having a negative sigma, right? It's a negative sigma going away from positive x-axis and stuff. And the center point is the mean, mu here, right? This bell curve is usually written in the form P of x, probability density function, is equal to 1 all over the square root of 2 pi, right? E to the negative x minus mu squared divided by 2 sigma squared. And you can see the reason why I brought this up is because there's a factor of 1 over 2 root pi here. So this root pi has actually applications in probability and statistics when it comes to calculating bell curves. Okay. I won't get into that right now. That's just one of the applications in probability. All right. So it's really interesting where this stuff can be applied in. Okay. All right. So let's move on. Now, I was expecting a more advanced audience, but some of you are or not. So do not attempt this problem here. Gamma of z times gamma of 1 minus z, proving that it's equal to pi over sine pi z. Okay. Not only would I not recommend people who don't have an undergraduate background, I don't even recommend people who have even multivariable calculus under the belt. You need to have at least complex analysis to do this problem. And when I mean complex analysis, I mean contour integration, up to contour integration. Otherwise, you can't do this. Okay. Now, if you have background in integral calculus and you're willing to build on the foundation that you have, refer to my other videos. Okay. So once again, if you have a background in integral calculus, you want to challenge yourself, the only thing you need to look at is another video on the beta function, and which I'm going to talk about in more detail in probably on Friday. Okay, this is the beta function. So you need to be equipped with that, and you need to be equipped with contour integration. Okay, even then it can be a bit challenging. Otherwise, don't attempt this problem here, proving gamma of z times gamma of 1 minus z pi over sine pi z. However, if you're a person who wants a challenge, go right ahead and do it. Okay. So go ahead if you want to take up that challenge. All right. Again, this is only this proof is for, to challenge yourself. It's going to be for homework. If you want to try it, go ahead and do it. And if you want to email me your results, you can email the results to it will be in the link below at the end of this live stream, in the description. My website, www.stem1online.com. If you want more information, if this is the right proof or whatever, you can send it to me. Otherwise, don't try this. Okay. Right. So as I said, you better have watched my other live show on the beta function, and then one on the gamma function. And on the contour integration, it makes you understand it into a really deep detail in order to do this proof. Okay. All right. So, and another thing too, as I mentioned, and I put it down here too. It's probably still better to watch one of the other videos on the beta function, but I also gave you a hint to use. You need to know what the beta function is. Okay, so definition 1, the beta function. Okay, so the beta function, known as capital B, as a function of both x and y. My multivariable function is equal to the integral from 0 to 1 of t, variable t to the power of x minus 1 times 1 minus t to the y minus 1 power dt. Okay, so you're going to need to use that, definition 1. And you're also going to need to use definition 2. Definition 2, the beta function identity. So b of x comma y is equal to the product of the gamma functions, gamma of x times gamma of y, divided by gamma of x plus y. Okay. So for those of you who watched my videos on the gamma function, you should be really fluent at this. You can calculate the beta function using the gamma function. Okay. So both these definitions would be handy in partly proving this product here. Okay, but otherwise may have a bit of a problem if you don't have that background. Okay. Anyways, let's move on. Okay, so we've talked about 7 as well. Next, differentiation under the integral sign. Let's talk about that. Okay, so differentiation under the integral sign. So those of you who have taken calculus 2, like finished calculus 2, and maybe into calculus 3 or some variation of it, you'll be able to understand this. Okay, so the differentiation under the integral sign. So this is all it's used for. You may be given a complicated integral. What I mean by that is an integral that cannot be solved in elementary methods. Okay, so given a complicated integral, capital I, let's say, this is definition 1. So given a complicated integral, capital I, define a parameter alpha. So define a parameter alpha such that your integral is now capital I as a function of alpha. In other words, what I'm saying is by defining a parameter alpha, creating a parameter, it could be alpha, beta, gamma, doesn't matter what you call it, z, by defining a parameter such that your integral is now I as a function of alpha, you are making your integral as a function of alphas too, not just as a function of x. Okay, so that can help you integrate your problem. Okay, so I as a function of alpha, then position your alpha in your function of that integral such that in the next step, you are able to differentiate both sides with respect to alpha. Let me repeat. Position your variable alpha such that in the next step, you're able to differentiate both sides with respect to the parameter alpha. Okay? All right. So that's part of the Feynman trick. This is called Feynman trick, differentiation on an integral sign, right? So you have your capital I, which is your integral, whatever you're dealing with. Obviously, it's an advanced, complicated integral that you can't use elementary methods, so you use this method, right? So you define a parameter alpha such that your integral is now I as a function of alpha. Position your variable alpha such that in the next step, you are able to differentiate both sides with respect to alpha. Okay. Then this would be like step 3, I say after anyways. After, simplify the expression such that it becomes simple to integrate. Okay, so after differentiating both sides, simplify it such that it's easy to integrate. You should be able to integrate it based off some sort of mathematical method that you already know. Okay. Hence the reason why my book is called Mathematical Methods, because it's so important. I feel like it's a good toolkit to have, especially if you want to build a lot in your calculus knowledge, or you just like major challenges. My book is what you want to get, especially for university. Okay, so and it will be in the description in the video below. At the end of the video, sorry, will be in the description. Okay, so for those of you who want to get the book. So next, next, we're going to clean up the term I prime of alpha, and we do that. Remember, it's I prime because they differentiated both sides, so it's now I prime of alpha by integrating both sides with respect to alpha. Okay. Then finally plug in the appropriate boundary conditions and solve for I of alpha, because you have to integrate both sides with respect to alpha. Okay. All right. So that's what we have there. And then we have definition 2. Definition 2 is just another part, the more formalized part of differentiating an integral sign, or also called Feynman trick. Right, Feynman, the theoretical physicist, if those of you who don't know, he came up with this mathematical method. Okay, so definition 2, given our integral capital I as a function of alpha is equal to the integral from x0 to x1, limits of integration, lower to upper bounds of f as a function of x comma alpha dx, which is a continuous function of both x and alpha, right? Because now I is a function of alpha, I define a parameter alpha. So if my function was already x, now it's x and alpha, right? Which is a continuous function on both x and alpha. Then differentiating both sides with respect to alpha yields capital I prime of alpha is d by d alpha of the integral of f of x comma alpha. I should be saying, so notice here, I should put my lower and upper bounds, x0, x1. So x1 f of x comma alpha dx, right? Because I'm differentiating both sides. I prime alpha is equal to d by d alpha, integrate from x0 to x1 of f x comma alpha dx is equal to the integral, again, x0 to x1 of di f of x comma alpha, di alpha with respect to x. Okay. So this is definition 2. This is like continuing on how it looks like mathematically more formalized when we differentiate under the integral sign. Okay. Now, the procedure is, for anyone who knows, how we can use the differentiating under the integral sign method or Feynman trick on the gamma function if we want to integrate. It's another way to integrate the gamma function. Okay. Right, so we know I'm going to write the gamma function again. Gamma function of z as an improper integral of x to the z minus 1 e to the negative x dx, where the real part of z has to be strictly greater than 0. Okay. So I should have said z here, doesn't matter. A gamma of n, where gamma of n is defined as the gamma function. Okay. So my question to the audience is, where should I place my parameter alpha so I can use Feynman trick and hopefully integrate easily? That is a question for you guys. See if anyone's coming in. Just 1 second. Let me see if anyone knows what's coming in. Anyone else? Yeah, I don't see it. Yeah, I don't see anyone else. Is anyone else coming in that knows about the gamma when it comes to the gamma function? So where should I place? Where should I place my parameter alpha so I can use the Feynman trick? Where can I place my alpha? Remember what definition 1 states. Right? We want to position our parameter alpha. We want to define an alpha. That's the point of this, to make our integral easier to integrate. We want to define a parameter alpha such that your integral, now I as a function of alpha, you position your variable alpha such that in the next step you're able to differentiate both sides with respect to alpha. Okay? So where would I place my alpha in order such that I can get my d by d alpha on both sides and then integrate after once I put the differential operator in and then be able to integrate with respect to x easily. So that's for you guys. It's for you guys to figure out. Okay, so die by, so I'm saying here, in other words, what I'm saying is when I do my die by die alpha, or I'll just say d by d alpha, right? In other words, d, let me put it down here, actually, I'm going to say d by d alpha of my integral from 0 to infinity, right? Sorry, I should be saying like this, I prime of alpha. So capital I of alpha, right? Initially, right? Because that's what we had. So I of alpha in this case is my gamma function, gamma of z, right? Usually when we have an integral, we say it's I. I represents integral. Here, since we have gamma of z, I of alpha is equal to gamma of z, and this is equal to the integral from 0 to infinity of x to the z minus 1 times, remember, I have to differentiate with respect to alpha after all this, so I need to place my alpha somewhere. Is it in the exponent? Is it, where is it? Anyone have any ideas? I think I got the audience a bit stunned, right? So, and that's the thing, right? That's what I mean by developing a mathematical intuition, right? You want to be able to think anytime you do a hard math problem, not just this, you want to be able to think multiple steps ahead, sometimes 6, 7, 8 steps ahead, and say, what am I looking down the road? And I want to be able you want to be able to pretty much you want to be able to pre-design steps. I'm trying to word it properly. Pre-design steps such that it leads you to that final frontier, if you know what I mean, right? You want to be able to have the variable such that that it's set up to work, right? So for instance, if I say I'm integrating from 0 to infinity of alpha, let's say here, I'm going to say x to the z, sorry. Sorry about that, x to the z minus 1, e to the negative alpha x dx. Let's say we had something like this, okay? The next step is to find the I prime of alpha. So for homework, I want you guys to tell me if I'm right or wrong. If I calculate I prime of alpha, and I take my d by d alpha on both sides, that's where this is, left-hand side d by d alpha, right-hand side d by d alpha, dot, 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 dot. If my integral, when calculating this integral, will it be able to integrate if I position my alpha over here? Okay, so that's for those of you who are going to want to take this up as a challenge. Okay. All right. So I hope that makes sense. Okay. So try to do that for homework. Right? So I really want you guys to do this for homework. Okay. So if anyone's interested in the chat, take that down. All right. All right. So the next thing we're going to move on to is the asymptotics and Stirling's approximation. It's another thing in my book that I'm going to talk about. It's a 322-page book. Yes, it's very rigorous. Okay, so we're going to look at the asymptotics. So we talked about differentiation. Integral sign, that's gone. So I'm going to say x's. So we're going to look at asymptotics and Stirling's formula. Okay, so let's talk about that. So asymptotics and Stirling's approximation. All right, so look at asymptotics and Stirling's approximation. Anyone know what this is? Anyone in the chat? Asymptotics and Stirling's approximation. If you've taken any statistics or probability in first year university, you come across it, okay? Now, you don't need to know the probability laws and formulas. That's not what this is about. We're doing calculus here. We're talking about the calculus behind it. Okay, so we're going to look at the asymptotics and Stirling's approximation. So in terms of definitions, right? So definitions for the asymptotics, right? So a function f of x, right, is asymptotic to g of x as x approaches infinity, as long as f of x over g of x approaches 1. Let me repeat. A function f of x is asymptotic to g of x as long as x is approaching infinity. Therefore, f of x over g of x approaches 1. Okay, that's what an asymptotic is. By the way, I should say fill in the blanks. So d by d alpha, I'm going to put it here in parentheses, fill in the blanks, please. So for anyone in the live show, fill in the blanks for homework, in the blanks, and send me your results to stemonline.com. In the blanks, please. The blanks. So dot, dot, dot. It's a mystery. All right. Hope that makes sense. Okay, so we're moving on. Okay, so we talked a little bit. So we're doing asymptotics of Stirling's formula. Anything else I have to talk about Stirling's formula? Trying to remember. Yes, definition 2. So we talked about definition 1. a function f of x is asymptotic to g of x as x approaches infinity, right? Right, so a function f of x is asymptotic to g of x as long as x approaches infinity of f of x over g of x approaches 1. Okay, so that's the first thing. Now, definition 2 of Stirling's formula states the following, that for large z, gamma of z is equal to, not equal, asymptotic to root 2 pi times z to the z minus 1/2 power, all to the 1/2 power e to the negative z, which is equivalent to n factorial. Remember, because gamma of z is just n factorial, right? So n factorial is asymptotic to root 2 pi n all times n over e to the nth power. Okay, so that's definition 2, definition 1 and definition 2 of Stirling's formula. Okay. So we're practically almost done, probably only like 10 minutes. The last part is going to be the physics applications, PDEs, quantum and probability, and research problems. All right, so I'm going to talk about this 10, 15 minutes, and then I'm going to get going, okay? So physics applications. All right, so let's talk about that. Now, I'm trying to remember, I wrote them down. Don't always remember all of my physics applications, but we're going to talk about them. Okay, so just 1 second. Let me see here. Nope, that's not it. Okay, physics applications. All right, so let's talk about physics applications. Okay, so let's do that. Let's talk about the physics applications. First, the heat equation. The heat equation comes up a lot with the gamma function. So heat equation is application of the gamma function. Okay. So heat equation. So note. Heat equation. Equation is used in the gamma function. Or to say is an application of gamma function. Okay, so that's one thing. Okay, the heat equation is the following. All right, so the heat equation, we're going to talk about that just 1 second. And that's going to be this guy right here. So capital K of x comma t, function of t, is equal to, always forget this equation, 1 over the square root of 4 pi t. Okay, so 1 over square root, so 1 all over the square root of 4 pi t e to the negative x squared all over 4t. Okay. So this gamma appears in normalization and higher dimensional areas. Okay, so that's number one. Number two, the gamma function is often used in quantum mechanics. So number two, okay, quantum mechanics. So it's going to be quantum. So it has applications in quantum mechanics as well. Okay, so in quantum mechanics, I'm going to use a different highlighter here. I'm going to use blue here, quantum. The mechanics. Okay, mechanics. So it's really interesting stuff, actually. So what you end up having here, right, is when you have Gaussian wave packets. Okay, so you have something called the Gaussian wave packets. Okay, and when you have a Gaussian wave packet, it does involve Fourier transforms as well. Evolve Fourier transforms. For those of you who don't know what a Fourier transform is, look at my other videos, live videos or regular videos. This would be one of the previous live videos. Fourier transform. And the following is this, right? So is the wave function, right? So it's psi as a function of x and t, right? Psi as a function of x and t is equal to an integral, okay, of psi of, I forget what it is, psi of k. Psi is a wave number of k. And then it's e to the power of I times kx minus omega t with respect to k. Okay, hope you guys are on the same page for most of you. All right, so that's one thing. All right, so that's a Gaussian wave packet. That's where they're also applied. It got automatically, if you have anything to do with the Gaussian, it's probably some sort of product or factor of a gamma function. Okay, and this is an application of it in quantum physics. Okay, this can be used in propagators, path integrals, all sorts of other things. Okay, and finally, I think we should talk about probability theory, maybe. 1, 2, probability theory. Okay. Yeah, probability theory 3. I'm talking probability theory is another application. So probability theory. Okay, this is also used there as well. Okay, when it comes to the Gaussian or gamma functions, is when you have something of this nature, right? If you had to calculate, let me think, something like this, if you had a improper integral, right, from minus infinity to infinity, maybe you're calculating some sort of probability where your random variable capital X is bounded between A and B. I need to make room here, actually. Okay, so P as a function of A being smaller or equal to X, which is smaller or equal to B, which is equal to the integral from minus infinity to infinity of f of x dx, where f of x is a probability density function, which I mentioned earlier, 1 over the square root of 2 pi sigma times e to the power of negative x minus mu all squared divided by 2 sigma squared. Okay, that's another example where you'd use this. All right. So that is it for today's live show. Okay, we're So we pretty much done a lot. This one was a very in-depth and very comprehensive review of the gamma function. But it will help anyone who had misconceptions, who already knew the gamma function, or for people who want to learn about the gamma function. Okay. All right. So let's look at one more thing. I'm just going to give these problems for homework if anyone wants to try, right? So these will be called viewer research problems. Okay, so viewer, let's do that. So viewer research problems. Okay, so this will be something that you should tackle for homework. Okay, so so this will be the last thing I'll input here if anyone wants to try these. Okay. So one of them is this guy right here. Okay, so I think this one is an appropriate one. Okay. This is challenge number 1. Challenge number 1 deals with, okay, so this is challenge number 1. So challenge number 1. Challenge number 1, the asymptotic behavior, right? So it's going to be find the, I forget this one, find the asymptotic expansions of the following. Okay, so gamma of z plus 1 over 2 divided by gamma of z. All right, so that's challenge number 1. Okay, challenge number 2. So that's challenge number 1. Challenge number 2. Evaluate asymptotically as t approaches 0 from the right of the integral over the real numbers. I think I had it here, e to the negative x squared divided by 4x. This is a 4t, sorry. Is that a t? 4t. 4t times f of x dx. That's challenge number 2. And then finally, challenge number 3 will be the last one. Number 3, okay, is study the asymptotics. Study the asymptotics of the following integral. Okay, this has to do with a quantum oscillatory integral. So this is I as a function of a is equal to the integral from minus infinity to infinity, right? Lower and upper limits of integration e to the I ax squared dx. Okay. All right. So those are the challenges that you should do. We'll take up hopefully all these or some of these on Friday. Friday is office hours. So what that means is anyone who has watched the live show right away or watched it after and they've tried the challenge problems and they want to ask questions on the previous live show, you can reach me in my office hours, 7 p.m. Eastern time on Fridays, okay, to ask questions. So once again, it will help if you can like and subscribe. Okay, that'll be very handy. Okay, and finally, let me see if there's anything else I want to mention. Let's see, anyone else is coming. No one else is coming, so I guess I should get going. So if you want to learn more when it comes to integral calculus to a research-ready level, right? methods, applications, and even open-ended problems for those of you who are extremely gifted. I can't do the open-ended problems. I put them in the book, see if anyone can do them. But I can't do them. Not smart enough for that. They're unsolved. No one can solve them. But I put them in because I thought I could maybe attract a certain audience who would like to solve those types of, try and solve problems that are unsolved. So again, if you want to learn integral calculus to a research level, ready level, methods, applications, open-ended problems, my book, Advanced Integration Techniques, is the roadmap for your success. Okay, you can buy it at my my website, right? The website will be linked in the description below for this live show. And if you just want personal tutoring, or if you want personal tutoring, I tutor undergraduates, and even some grads too. You can apply at www.stem1online.com. That'll be in the description as well. Okay, the link. Anyways, that's it for today. Have a great day. Have a good night, guys. And I'll see anyone on Friday. All right, so that is it. Bye-bye.